Hello there, and welcome to Tools Tuesday here on Answer Everywhere. Today we're taking a look at the source code for Git, the ubiquitous distributed source control versioning control system. So Git is everywhere, and you've almost certainly used it. And today we're going to focus on the data structures of Git, kind of how it deals with trees, what it does with those trees, where it stores objects, those sorts of things. And we're going to deal less with the higher level API of commands and how they work. We saw a little bit about Git internals yesterday when we looked at the Gerrit code collaboration, code review suite that's built on top of Git. And one thing we saw was that Gerrit stores a lot of its data, or basically everything it needs for a database, inside of Git refs. And so we played around a little bit with Git refs. And today we're going to look deeper at what refs are and how they work, as well as all the other kind of Git internal stuff. Before I begin, maybe I'll issue my normal proviso, which is that this is a live show. It's an improvised live show. You can join in and watch. And every weekday, we jump into a source code repository that I'm unfamiliar with. And we kind of just poke around and try to see what we can find. The idea is to kind of simulate working in an environment where there's so much code that no person knows it all. And on any given day, you may have to figure out the inner workings of a complicated system without necessarily access to good documentation and not necessarily with the luxury of being able to do a bunch of research ahead of time on how things work. Now, obviously, there's an advantage to if it's a system you've used before, like Git. So it may be that we find our bearings quickly. It may not be. We'll see how it goes. So I'm in the Git mirror, which is in github.com/git/git. And I don't know where the official source code repo lives. It may just live on Linus's laptop or on some machine that's controlled by Linus or the current core maintainer or whatever. But I do know that you mail changes, and there seems to be this git gadget thing, which you can link to here, that will allow you to somehow turn pull requests into patches that go to the mailing list. Some kind of integration between the world of the open source social GitHub ecosystem and the Git development world that still uses more old school tools. So we are in the mirror, and here's the root directory. And we see lots of files, lots of C files in the root directory, which is not the least bit surprising. It's also, I guess, good to look at languages. Only 50% C, which I find very surprising. There's nearly 40% shellcode. There's some Tickle, I think that's how you pronounce it, and some Perl, some Python, and some kind of like make stuff, and probably documentation stuff. Kind of fills out the rest. So I was not expecting to see this much shell. I'm not sure how much of the shell we'll see, but my understanding, the high-level architecture of Git is that conceptually it's a little bit like a file system. When Linus first started implementing it, the thinking was he had lots of experience with the Linux kernel, and he was going to make kind of like a file system-y, low-level API for handling source code and doing things like creating hash trees. And then on top of that would be utilities to expose a nicer programming API. And this is perhaps what is meant by a Git porcelain. I'm not entirely sure, but that's sort of how I recall it breaking down. So we'll probably mostly focus on the C, but As we look through, we'll see if we can find out where the shell scripts are and the sorts of things that they're doing. So looking through the folders of the root directory, we see some documentation, which we will ignore. Block SHA-1 might be important because blocks might be important, but I guess we'll leave that maybe toward the end. Built-ins, I'm not sure what they are. CI is presumably continuous integration. Compat and contrib, we can probably ignore. I have no idea what EWA is. I guess we'll look at EWA. Git GUI and Git K and Git Web are all user interfaces to Git. Git Web is, of course, so I think we've seen lots of Git Web installations, mainly from like GNU, Free Software Foundation type repos. I'm not entirely sure what Git GUI is, but Git K is a nice utility that has I guess a GTK interface to Git. Merge tools might be more like utilities. Negotiator, I'm not sure what it is. Perl, I don't really know what they do with Perl, but we'll take a quick look. And then the important things I think are going to be things like refs and ref table. SHA-1 and SHA-256, I'm going to guess are things we can black box because those are standard algorithms. They're not unique to Git. Who knows what T is? I guess we'll look at T and templates and trace. Not trace. And then it looks like usually when a repo is structured like this, a lot of the important files are in the main directory. So we're going to leave the main directory and take a quick look at these folders and see what we can eliminate quickly. And then if we can't eliminate something quickly, we'll come back and take a quick closer look at it. So this will be maybe like an initial quick triage. And then after the quick triage, we'll go and build kind of the priority queue of files to look at. So here's EWA. There's EWA IO, RLW, and EWOC. I was wondering if EWA was related to EWOCs. So I guess let's look at IO. Something about serialization, and it's including ewoc.h. Let's look at ewoc. Do not use built-in pop count TLL. The GCC implementation is notoriously slow on all platforms. EWA bit pop count. And then there's some low-level bit stuff. Allocate a new EWA compressed bitmap. So something on bitmaps. Is EWA something that is general? Is the Cherokee spiritual beliefs? Probably the source of the name. In EWA bitmap, the nth bit marks whether the nth directory has valid untracked cache entries. In EWA bitmap, the nth bit records check-only bit of read directory recursive for the nth directory. I think I'm supposed to see some context here and not just read it from there. Okay, so somehow these are bitmaps that record things like the bits in the directory. The bits in the map somehow enumerate directories, and they're set to 1 if something or other is true. And so this is some kind of data structure that I think we can ignore for now and just consider it in implementation detail. Negotiator, I'm not sure. We'll look at default.h. Default negotiator init. And struct fetch negotiator. Is it negotiating like authentication? Let's see. What does default implementation do? Revlist push. Negotiation state. Yeah, I'm going to guess this is for pushing. This function marks a rev and its ancestors as common. In some cases, it is desirable to mark only the ancestors, for example, when only the server does not yet know that they are common. So this does seem to be something about remote, coordinating with the remote to send files and only the appropriate files. So we'll leave that, we'll ignore that. Here's git.pm, maybe PM is Perl module. I don't read Perl, so we'll see what we can find from this. This is the Perl interface to the Git version control system. So this, just taking this comment at face value, seems like Perl bindings to Git. Methods which can be called as standalone functions as well. Command one line, command noisy. This module provides Perl scripts. Easy way to interface the Git control system, the Git version control system. The modules have an easy and well-tested way to call arbitrary Git commands. In the future, the interface will also provide specialized methods for doing easily operations which are not totally trivial to do over the generic command interface. Okay, so these are, I'm going to think of them as bindings. Here's refs, which I think will be important. Ref tables, which I think will also be important. Here's T, and GitHub is apologizing to me. GitHub is saying, sorry, we had to truncate this directory to 1,000 files. Well, these are T something or others. T and then a number. Lib diff alternative pager, Perl. And a bunch of T's. And these ones are shell scripts. But I don't know what the T's stand for. Let's pick T5000. Got huge object, pax.tar, and huge and future tar. What if I click on huge object? Yeah, GitHub's not gonna show it to me. Understandably, because it's supposedly huge. We get a README? We do get some sort of README. Let me find the top of it. This is a long README. Okay, core git tests. Okay, so these are tests, I suppose. This directory holds many test scripts for core git tools. The first part of this short document describes how to run the tests and read their output. When fixing the tools or adding enhancements, you are strongly encouraged to add tests to this directory to cover what you are trying to fix or enhance. The latter part of this document describes how your test scripts should be organized. So perhaps these tests or similar things to these tests correspond to or account for a lot of the shell scripts. Oh, hey, Raxnef. So Raxnef is saying T may stand for test. I don't know. Yes, it does stand for test. You probably said that well before I figured that out. But that was a good guess. So, and then we have templates. And the templates seem to be things like hooks. Like hooks pre-push sample, rebase sample. So these are, I guess, sample hooks. Or you can, I guess, maybe copy them and do something with them. How about a pre-commit sample hook? Just take a quick look. It's a shell script. To enable this hook, rename this to pre-commit. We've got if git rev parse verify head with output into dev null. I guess if this returns a success condition, is that what this is testing? And then against equals head. Otherwise, I guess the initial commit diff against an empty tree object. Against is equal to the empty tree object. And then where's the actual hook? Okay, so this is doing this test for allow non-ASCII. And then it's going to say exec git dist. If there are white space errors, print the offending file names and fail. And it's calling exec here, and it's computing allow non-ASCII here. But I don't actually know where it's hooking. What this git diff thing? I guess it's hooking because of the name. Something might be looking for this name and executing this script if it's found. So maybe there's nothing here that like registers in a hook except for the naming convention. Perhaps, because I don't see anything that looks registry, but I could be missing something, so I'm just looking quickly at this point. All right, so we've got refs and ref table, which we're going to look at. And then we've got a bunch of C files and header files. Let's see what we can find. This is so big that it might be worth looking in something other than GitHub. But I'm going to persist with GitHub for now. All right, so let's see. So tags are obviously going to be important. I think for a lot of these, I can probably just open up the header. Tree diff and tree walk. Yeah, tree. What I want is tree and tree walk. And maybe tree diff. So normally I open up a ton of files and process them in order. But I might just stick with a smaller number of files and then come back to them. But I guess before I do that, let me do a quick scan. So sig chain is probably signature train, right? How do I make how do I make Firefox not open these in order? Let me see if I can do this. So I don't know what the right search term is. Open tabs on the right by default. There's some setting about config. Yeah, related. Yeah, okay. There we go. All right, so I hope that fixes it. Okay, so let's start with, let's gonna start with tree.h. And then where's tree diff's implementation? Did I open that? Oh, I think tree diff is just a C file. And then maybe we'll look at walk. Tag should basically just be a ref. So maybe I'll see if there's a ref.h or ref.c in the main folder. Here's reset, resolve, undo, revision. Do I want revision? I guess I want revision. Refs and refs.c. I want. Reflog walk looks fun. Yeah, I guess we'll look at the implementation. Rebase, I'm curious about. Reachable should be whether something is reachable. Prune packed, I'll open. So I guess I am going to open a lot of files. There's a priority queue, which should probably just be a pretty standard priority queue implementation, unless it's a very fancy priority queue implementation, which you would not be surprised, given that it's originally a Linus repo. I'm going to open pack. So what I understand about how files are stored, and I'm not sure this is correct, is that Git initially starts by storing at least the contents of files in a content addressable way. So it'll take whatever's in the file, like if I have pager.c, and it's the initial commit, it'll hash the contents of pager.c and store that hash under the .git directory somewhere, using its SHA-1 hash, unless Git has graduated to like SHA-256 or something like that. And then periodically, and I don't know what the period is or what triggers it, it does some kind of garbage collection where it takes all the hashed files and like compactifies them into something that's essentially diff encoded. So it'll store like maybe an initial file or initial snapshot, and then additional files will be stored based on their diffs from those snapshots, and that just reduces the amount of data stored on disk. And I think even when it stores the original hash, it stores the like the zlib compressed data rather than the uncompressed data. But that's more or less how it's done. What one question I have is that there's some algorithm that determines whether two files are the same file. Like if you move a file, then Git knows, I guess, based on its content. If you just do a straight move, by which I mean renaming the file, then Git will know that that's the same file, and you can ask it to kind of track that file through history over moves. But if you also like take the file, move it, and change a couple of lines, then Git somehow knows that it is the same file, even though the hash is different and the name is different. So somehow it's got to figure out some sort of distance function. And I think if I remember correctly, it's something like if I'm looking for bar.c or whatever, the new file is called bar.c and it used to be called foo.c. It looks for places where bar initially appeared, and then in the previous commit, bar wasn't there, but foo was there, and then foo disappears in the next commit. So that's one candidate for a moves file, and then maybe it computes like a distance among all of those candidates. I would like to see what that algorithm is, and maybe it's under revision or something, but I'm not sure where that is. Notes, I think, are kinds of refs that you can store. Merge sort. That's cool. Should we open this just for sport? I guess why not? Here's some mail map stuff. List refs, log tree. I'm guessing this is a tree of logs as opposed to log running time tree algorithms. LL merge, list objects. Levenstein, that might be like a distance function. I guess let's look quickly at Levenstein. Am I in private? Levenstein's going to take two strings. Something about swap penalties. A metric for comparing two strings or words. Levenstein, yeah, the distance, information theory distance. A string metric for measuring the difference between two sequences. So Racksnap says Git uses SHA-1 hash to hash all files the same content. Yeah. All right. Yeah, so that's the content addressing stuff I was saying before. You know what? I'm going to look up whether they at least optionally use other hashes. I don't know if there are security implications to SHA-1 collisions in Git, but I wouldn't be surprised if there are. Okay. So how are we going to compute the string? Lev of A, B. There's these two conditions if either string is 0. Otherwise, we're going to, I guess, recursively call lev on the tail of A and B if the first two entries are identical. But if they're not, the first two entries are not identical, we're going to take 1 plus the min of these three things. One is take the tail of A and lev it with B. The other is take A and lev it with the tail of B. And the other is to lev the tails of A and B. Okay. That's some distance function. Hello, Fasogos. Okay, so let's do, does Git use SHA-256? Git and SHA-256, why doesn't Git use a more modern SHA? So performance. Okay, it will. And Git 2.16 is the first release to illustrate and implement that intent. Note, see Git 2.19 below. It will be SHA-256. Okay, so this person claims that Git uses SHA-250 or can use SHA-256. So objective: migrate SHA-1 to a stronger hash function. Yeah, okay. So at its core, the Git version control system is a content addressable file system. So content addressable means you basically you take hashes and the hash is the identifier rather than a file name. It uses the SHA-1 hash function to name content. Okay. Choice of hash. Yeah. Okay, what's the status though? We're not gonna look at the implementation details. Whatever happened to SHA-256 supporting Git? There is no interoperability between SHA-1 and SHA-256 repositories yet. Okay. So I'm not sure. It seems seems like maybe it works. Hello there. Oh man, I can't read this Cyrillic, but I think that hi. I was gonna try to read this, but I think it's too. Um, I at one point learned a tiny bit of Russian, but I've forgotten everything everything that I've learned. I don't think I ever really got past the alphabet and like basic words like cat and dog. But hi. Um, okay. Let's see. Where were we? Okay, so yeah, so we're using SHA-1. Oh, there is SHA-256 here. I guess maybe that settles that question. But I'm not sure how often it's used. And maybe if you have like some sort of like Bitcoin ASIC that does SHA-256 quickly, maybe you can use it for your Git repository. Nikito Simonenko. All right, great. And Google Translate. Thank you. Nikita. Welcome, Nikita. Yeah, I thought the H thing was an N, but that's where I kind of lost my nerve because I wasn't sure. Nikita. Okay, so this is N, and this is like the second letter, which looks like a reversed N in the what is our alphabet? Arabic or numerals or whatever our alphabet is. The English alphabet is called. So that's that's kind of like an E, and then the rest it makes sense. Nikita. This is Nick. Okay, hi Nick. All right, cool. Okay, so let's see. So AppSec, interesting. I guess maybe this is like checking integrity. Oh, maybe like is Git literally a file system? Can I mount it as a file system? I'm sure there are like fuse file systems that let me do that. Diff might be really essential, but I'm not sure. Delta might be really essential, but I'm not sure. Decorate is presumably some way to decorate things. C type I'll ignore. Daemon I think is for serving Git repositories over the internet. And connected, I don't know what these are. These could be for network connections. These could be some sort of computation about whether like two subtrees are connected. I don't know why they wouldn't be. Config, I think we could ignore. Commit is pretty important. And commit slab, commit graph, column and color, and chunk format. I guess I do want chunk format and maybe CB tree. Bloom, I'm going to guess is like a Bloom filter. And blob, I think is what, blob is the name of like a file blob is the file content stuff that's named by the hash, I think. Bisect should be support for Git bisect, which is a beautiful tool for figuring out which commit introduced a bug or a failure. And then apply. Is apply a Git command? I'm not sure. An absolute path. Okay, so we got some stuff. I put a bunch of important stuff at the end here. So maybe I'll make a new tab. Whoa now. I'll put this important stuff in the new thingy. I guess I could do without CB tree, but and what I really want is commit. Okay. For everyone who's watching this, asking why I don't just use a code editor and do this, there are lots of reasons. One is simplicity. When I started out, kind of everything was breaking at least once per episode. And so it's just, the browser very rarely breaks. GitHub rarely decides to stop serving you things. And I'm also doing these in a very restricted and not very set up VM. So I don't have all the fancy tools. I mean, I certainly don't have any tools that require me to be logged into anything. But that being said, we're going to build out some tools for doing like LSP, language server protocol stuff. But we're going to kind of build them out as we go. And the idea is to show, to show how they work. because that's what the show is about. Okay, so I'm going to move. Let's see. How am I going to do this? So let's look first at this, which is tree. Is tree more fundamental or commit? Let's look at tree. I should definitely try the command git cat file p SHA-1. Like a commit, for example. Okay. I could try pressing the button to get the editor in the browser. I can't do that here because I'm not signed in. I think you need to be signed in to get, GitHub has some sort of built-in editor right now because, yeah, I tried. So thank you, Fastigos. I tried this before. You're required to be logged in, and I'm not logged in on GitHub. So that's part of the. That's really just simplicity because I don't want to. I don't have authentication stuff here if I don't absolutely need it. But the Racksniff was saying try git cat file p on SHA. Okay, I don't know how to find the. So let me go into git. So let's see if I can get this SHA-1 sum of some file. What about ws.c? And I'm not sure that. I mean, maybe the hash of that git uses hashes the file with some other stuff. So I'm not sure if this is going to work, but we'll try this. Not a valid object name. But if I go into the .git directory, maybe I'll switch to Emacs here. We have looked at the Emacs source code. So there should be a .git here, right? So here's .git. And we have branches, config, description, head, hooks, index, info, logs, objects, and refs. Objects should be where stuff is stored. Pack, I believe the pack files are these diff encoded files. I don't know what info is. And I only have two pack things. I have a pack index, which probably there's nothing really to render here. And I have a pack.pack, which is the index is presumably the index into the pack. And the pack is presumably the diff encoded stuff. Okay. Has to be an object hash in a Git repo. Yeah, I don't know. I think I have no objects. I could try creating a new. Repo so that not everything is packed. Wait, compressed to? No, what have I done? Here's Garrett. Does Garrett have any objects? This looks like a hash. I might have to. Okay, so git. What was it? Cat file p of this thing. I feel like I want that to be an object name, like a git commit. Okay. Yeah. Grab this thing. Oops. I think I've mixed up my metaphors here, and I ran a shell command in Emacs, and I didn't mean to. Let's try this again. I'm not sure that's going to work on a log message, but let's try it. Git cat file p. Yeah, okay, so I do get the log message. Okay, and what do I get? I get a tree. Maybe this is the root of the tree. This is probably the parent of the commit. Let's see if we can find that. So 0607 is the commit I looked up. So its parent should be the thing before it. Let's see if the parent is 8983. Whoops, that's not what I meant to do, just log. So here's the, okay, so here's 0607, which I catted, and here's the parent commit, 8983, and so that is what the parent is. And then the author and the commit, etc. And then signed off by is just some metadata. That's how it is actually stored. Yeah. I'm not sure though why when I asked for, I just pulled some file name from the object storage. I'm guessing that's not actually a SHA hash of anything, but it didn't want to cat that. It didn't find whatever I thought was a SHA hash. Or maybe I asked it in the wrong directory or something. Okay, so let's get to the code, I guess. So here's the tree.h. So we're going to include only one thing, which is object.h. And we've got lookup tree, which takes a repository, and an object ID, which is what OID stands for. And it's going to, I guess, return a tree, or rather a pointer to a tree. So you can, given a repository and an object, we can look up, I guess, what tree it belongs to. I don't know if this is the root of the tree, or if it's just a like the connected component of the tree, and then later we can walk up to the root if we need to. We can parse a tree buffer, given a tree item and a buffer and a size, and then we get an int. Maybe the buffer is an in parameter that contains the tree information, like for storing the disk or whatever. And the thing we get, the out parameter might be the first thing. You can parse a tree gently. And we get a tree. We pass in a tree or like a tree pointer and some int quiet on missing, and we get an int back. And I don't know what happens, or I don't know what the parsing actually does. And then we've got this parse tree inline thing, which takes a tree. It's going to return parse tree gently with 0. And we can free a tree buffer. So this says buffer, and it's a tree. So maybe, I don't know what the difference between these two things are up here. We can parse it. So this is all like parsing, and we can read tree at, so given a repository and a tree, and something about a base. I don't know if a base is like a root, and a path spec. We're going to call this like internal thing, some function, some read tree function with a void context. And then we've got a read tree. I don't know how enlightening that was, but let's see if we can look at the implementation. Tree.c. And we're importing more stuff, including tree walk and repository, which is not so surprising, and object store and commit and tag. So this is not the lowest level thing, obviously. So let's see, read tree at. Okay, I'm kind of curious about what it's doing when you're actually calling parse tree. So when you call parse tree buffer on a tree, which is called item and a buffer and a size, we're going to call item object.parsed. Oh, okay. So if the tree already thinks it's parsed, maybe we return 0. Otherwise, we set object parsed to 1. We set the tree's buffer to buffer. And we set the tree's size to size, and then we return 0. Maybe instead of reading this as a command to parse a tree, maybe I should be thinking of this as a parse tree, as an object? I don't know. So parse tree gently is going to take a tree and quiet on missing. I hate when dark mode. Yeah, sorry. It is annoying. It annoys me too. But I don't have a great workaround. I know GitHub has a dark mode, but again, I'm not yet logging in. Maybe at some point I'll log into Git mode, into GitHub. But I also look at a bunch of stuff that's not GitHub. Okay, so if item object is object.parsed, return 0 again. Otherwise, we're gonna read repo read object file, given the repository in some object.oid, and a type and a size, and we're gonna set the buffer to that. And if we don't get a buffer, we'll do some error stuff. If type is not object tree, we're gonna free the buffer and error out. Otherwise, we're going to call parse tree buffer with the buffer, which again just sets some stuff. It just gives the buffer to the tree, it looks like. But it doesn't necessarily do any parsing. All right, so I don't have a good sense of like what, this doesn't really seem to be like running a parsing algorithm. Here's a call to parse object, repo PL type. Okay, I don't know. So I'll just, here's read tree, which just calls out to read tree at. Is this a parsing algorithm? Read tree at, let's see. While tree entry, desk and entry. Desk is what? Description. We're gonna check if the return val is not equal to all entries interesting. Then we're gonna call this tree entry interesting function. And do some stuff. And then we're gonna switch on whatever function we passed in. We're going to give it the OID, the base, the entry path, the entry mode, and the context. And I guess the function's job is to eat all of this stuff and return something that we can switch on. And the function will decide whether to return 0, in which case we continue. Or it can return read tree recursive, in which case we break. Or otherwise, whatever function returns, we return -1. We're going to check if something s is dir entry.mode. So if we're a dir, we're going to OID copy. I don't know which copies to which, but maybe we'll copy the OID to the entry OID. Otherwise, if it's a git link, I don't know what a git link is. Maybe something like a symlink. Maybe just some kind of git pointer. Then we're going to create an empty commit pointer or something. Then we're going to look up the commit from the entry OID. And if we don't get a commit, we're going to fail. Commit in submodule path. Maybe git link is a submodule link. Otherwise, we're going to like parse it into the submodule, I guess. And then length is tree entry. Yeah, I don't have a good sense of what is going on with these trees. This doesn't look like a standard tree parsing thing. I think that the real action is maybe happening elsewhere. And this is maybe like kind of like setting the stage, putting things in place for some other real algorithm stuff to happen, like tree walk. So let's see if we use tree walk anywhere. No, but we import it. Let's see if I can find tree walk. Did I move that to this other thing? No. But I bet it's just in this directory, right? So let's see if we can just do tree-walk.h. Yeah, sorry about the blinding whiteness. Magic. Yeah, there's lots of magic. Omega Lil. Okay, so here's tree walk. A tree walking API is used to traverse and inspect trees. Here we go. An entry in a tree. Each entry has a SHA-1 identifier, path name, and mode. We've got this struct, which is a name entry. It's got an OID. It's got a path length, and a mode. So the OID, I guess, is the SHA-1 thing, but it may be generalized to SHA-256. Then tree desk is a semi-opaque data structure used to maintain the current state of the walk. Okay, so the desk, maybe description or descent, has information about kind of like the state used for tree walking. So the buffer, a pointer to the memory representation of the tree. Okay, so this is the memory representation of the tree. It always points at the current entry being visited. Okay. So buffer is not always the whole tree. Buffer is indexing into some larger buffer. I'm not sure if we keep a copy of the whole buffer anywhere, but it's always pointing to the current entry. And then name entry points to the current entry being visited. Wait, what? It always points to the current entry being visited. Name entry points to the current entry being visited. Presumably the name of the current thing being visited. I don't know. Size is the number of bytes left in the buffer. And some flags. About whether to do it gently. And something about raw modes. And one shifted over by 0. So I remember now that left shift multiplies instead of divides. Because my mnemonic now is that this is like stream writing, and we're writing things to the stream. But what I don't know is what happens if you do 0 of them. That should mean append like 0 zeros to 1. Is that right? Let me see if I have a calculator. Yeah, so 1 left 0 should be 1. I don't know. Maybe things are just in this format, and they're using 0 as like the base case, so it's easy to read if you're used to reading like this sort of thing where there's more shifting going on. I don't know. If you have a sense of why we're doing 1 left shift 0, let me know. Okay, so tree entry extract, decode the entry currently being visited, the one pointed to by the tree dex entry member, and return the SHA-1 of the entry. The path P and mode P arguments are set to the entry's path name and mode respectively. Okay. So this is length stuff. Do we have anything that looks like oh, this is the header. Okay. So I was going to see if I was going to look for something that looked like a standard tree algorithm, but that's going to be in the C file. But yeah, so this is where the tree stuff is. And traverse tree is going to traverse n number of trees in parallel. Oh, wow. Traverse trees. The function callback member of traverse info is called once for each entry. So let's read the comments on tree entry and tree entry gently. Visit the next entry in the tree. So this is visiting one entry, I guess. Returns 1 when there are more entries left to visit, and 0 when all entries have been visited. This is commonly used in the test of a while loop. Yeah, okay, so that's what we saw, I think. And then we have, you can initialize tree description. All right. And then we have some traverse info, a structure used to maintain the state of a traversal. Okay, and we've got a path. Traverse info prev, I guess previous, points to the traverse info which was used to descend into the current tree. So yeah, I'm going to guess desc is descend. If this is the top level tree, prev will point to a dummy traverse info. All right. We have an entry for the current tree. If the tree is a subtree, we've got length and mode, path length, which is the length of the full path for the current tree. Path spec. I don't know what path spec is, like some specification. Okay, and then we have something df conflicts. Can be used by callbacks to maintain directory file conflicts. To maintain conflicts. Do you want to maintain conflicts? I guess maybe when you are when you have to resolve, like manually resolve conflicts, maybe it's referring to maintaining the data structures or the files or whatever that are used to tell you that there are conflicts. And then we have the traverse callback, which is function. This is the thing that we saw in the header file. The arguments passed to, or we saw it in some file, I guess tree.h or something. The arguments passed to the traverse callback are as follows. N counts the number of trees being traversed. All right. Mask has its nth bit set if something exists in the nth entry. That's just true of that's just true of any bit set. Is something the nth entry of what? Is this the same n? Does it mean like the nth entry of the tree? And how would you know that if you haven't traversed the tree yet? And that I'm not sure of. Dir mask has its nth bit set if the tree's entry is a directory. These kind of look like the EWA stuff we saw. Entry is an array of size n, where the nth entry is from the nth tree. So maybe these n's, so an array of size n. I guess so one entry per tree. And maybe that's what mask and dir mask refer to. I don't know. And the info maintains the state of the traversal. Okay. Returning a negative value will terminate the traversal. Otherwise, the return value is treated as an update mask. Okay, so if you return negative, we're done. Otherwise, you return some mask, an update mask. Okay, and what did the mask say? If the nth bit of the mask, presumably, I'm going to add of the mask, is set, the nth tree will be updated. Okay, and if the bit is not set, the nth tree entry will be the same in the next callback invocation. Okay. So it tells it something about whether that particular tree is going to be updated. Yeah. Okay. So Racksnap says he guesses that they're using the left shift by 0 for style. Yeah, I'm guessing style too. That's that's good to know. I was just totally guessing, but I think Racksnap is better versed in code like this. I don't know. Is that true? You seem to know. you seem to be more oriented than I am and stuff like this. Okay, and then we have some stuff like some data and show all errors. Okay, so this looks plausibly like a real tree algorithm. This code all looks nice. You can tell that the people who are making Git are intelligent and experienced people. So here we are in treediff.c. Treediff.c. We get a comment saying an internal mode marker saying a tree entry is not the entry of TP of I'm in. The LL diff tree paths for what it means here, and we will update use emit entry for diff only if it unset. So now we are entering the land of I think we're like rolling up our sleeves and getting serious. Variable names are getting shorter, like X and NR. We've got some direct calls to the allocators, including, I guess, allocating an array. LL, some like left, I don't know if it's left leaning, some left, I guess, parsing thing. Diff tree paths. Is this the same as like, yeah, I forget what LL stands for, even though I just looked it up yesterday. Okay, so yeah, okay, that makes sense. But so he says he's done a lot of binary stuff. Okay, yeah, that's good. That's good. Okay, LL diff tree OID. Let's look up LL again. I assume it's the same as the LL parser. Leftmost derivation, left to right. Why is it LL? Left to right, performing the leftmost derivation of the sequence. Okay. It parses in LL regular language. Just curious if it means anything else in. So we have AVL trees. We have the LL rotation, left rotation, LL. Why is it LL? Not just L. Okay, match case. Okay, match casing. All right. Well, whatever it is, it means left. We're gonna do left stuff first. Okay, so compare two tree entries taking into account the only path or S is dir mode, but not their SHA-1s. Okay, so we're gonna ignore the content. We're gonna keep track of their path, I guess, and whether they are a directory. Files and directories always compare differently, even when having the same name, thanks to base name compare. All right, thank you, base name compare. So empty stuff, take part in comparison as plus infinity, so that they sort after valid tree entries. But I guess they are, yeah, I guess if something's invalid, it doesn't matter their relative sorting. They're just always after stuff. Due to this convention, if trees are scanned in sorted order, all non-empty descriptors will be processed first. Cool. All right, so tree entry path compare is going to take two tree descriptors, or descents, I guess, as we decided desc was. It's going to create name entries and an int, I guess, comp for the result. Yep, it's going to return comp. Okay, so we have empty descriptors sorted after valid tree entries. So this is just redescribing what was up here in the function comment. So if we don't have size, we're going to return T2 size. Okay, so if T1 doesn't have a size and T2 doesn't have a size, we will return 0. But if T1 does have a size, we'll return 1. And I guess this is a compare function, so that means that 1 is the second entry is bigger, I think. Otherwise, if T2 doesn't have a size, we'll return -1, because since we're here and this didn't execute, T1 does have a size. So T1 is bigger, I think. And then we're going to set E1 and E2 to the relevant entries. Then we're going to call base name compare on E1 path, tree entry length E1, E1 mode, and E2 path. And then we're going to return the result of base name compare. So really the work is being done by base name compare. And this function just handles edge cases, it looks like. We get a bunch of other things like emit diff first parent only, convert path to opt diff callbacks, emits diff to first parent only, and tells diff tree walker that we are done with P and it can be freed. All right, path append new, make a new combined diff path for path mode SHA-1 and append it to the path list tail. Okay. All right, so these are tree diffing algorithms. New path should be added to combine diff. 3 cases of how it should be called and behave. Emit. I don't know what it means to emit a path. What are we returning? A combined diff path. All right. We've got generate paths. Okay. So this is tree stuff. We may come back to it if we need to learn more about the tree stuff, but let's move along and see what other low-level stuff we have. I think I already looked at tree walk when I was trying to understand what was going on with tree. Yeah, pretty sure. Filled tree descriptor. Initially, yeah, it is descriptor, not descent. Initialize a tree desk and decode its first entry given the object ID of a tree. Returns the buffer member if the latter is a valid tree identifier and null otherwise. So it takes a repository and a tree descriptor, and it's void. So I guess it's going to return the tree descriptor. Or no, it's going to just initialize it. So I guess that is the out parameter. It's going to take an OID. Decode its first entry given the object ID of a tree. So the OID is like a reference to the tree itself, I guess. Maybe stored on file, because I think object IDs are SHA-1 hashes. And then we have the struct traverse info, which I don't think we looked at. But it's what? Does it have like members? We have a traverse tree callback. Okay. Oh, here's traverse info. I don't know why it's declared here so that we can type def this thing, this callback. And then the actual implementation is here, a structure used to maintain the state of a traversal. This is interesting. So we've got a traverse path. The previous, is this we looked at? We might have looked at this. Path spec. Yeah, we did. But what we haven't looked at is path spec. See if we can find path spec. Let's see if we import anything that seems like it would have path spec. All right, let's, what if we just grep struct path spec? And let's grep it recursively. Yeah, but I want, let's see. Is it gonna do that? That looks promising. Let's try pathspec.h. Pathspec.h. So here we are in Emacs. Here we go. Here's the pathspec struct. See glossary context.txt for the syntax of pathspec. In memory, a pathspec set is represented by struct pathspec and is prepared by parse pathspec. So I just want to know what a pathspec has. It's got nr, whatever that is, whether it has wildcards. I guess a recursive int, recurse submodules. These might be booleans, essentially. Unsigned magic, max depth, and then we've got this pathspec item. And it has car stars, which are essentially strings. It's got match, original, magic, length, prefix, no wildcard length, flags, attribute match, NR. And then we've defined attribute match here, which is a value and some essentially, literally an enum, match set, match unset, match value, match unspecified. Okay. I have, I don't feel any more enlightened, but that's what a path spec is. It did tell us to look in this text file, right? Glossary context. Let's see if this is in this repo. What if we do find to documentation. Here's the glossary. Let's see if path spec tells us anything interesting. Pattern used to limit paths in Git commands. Pattern used to limit paths in Git commands. So it's used to limit it. Paths are used on the command line of the git ls files, git lstree, git add, and git grep, git diff, git checkout, and many other commands to limit the scope of operations to some subset of the tree or working tree. See the documentation for each command for whether paths are relative to the current directory or top level. The path spec syntax is as follows. Any path matches itself. The path spec up to the last slash represents a directory prefix. The scope of that path spec is limited to that subtree. The rest of the path spec is a pattern for the remainder of the path name. Paths relative to the directory prefix will be matched against that pattern using fnmatch3. In particular, star and question mark can match directory separators. For example, documentation /star.jpg will match all JPEG files in the documentation subtree, including documentation /chapter1/figure1 JPEG. The path spec that begins with a colon has a special meaning. In the short form, the leading colon is followed by 0 or more magic signature letters, which optionally is terminated by another colon, and the remainder is the pattern to match against the path. Okay. So this should all be visible. Since this is used by commands, I should be able to look up git path spec and find like examples. So git ls files. So yeah, so this is kind of like bash file globbing and related stuff, but unique to Git. Okay, cool. That's what path spec is up to. Here's tag. I think before tag, I kind of want ref, but let's look at tag first, I guess, since I'm already here. So we're just going to include object. And a struct tag has an object, another object, which is called tagged, and a string tag, and a date, which is a timestamp. We can look up tag, parse tag buffer, parse tag, release tag memory, and deref some stuff, and we've got some sort of GPG support. Okay, so I think tags are commonly used for signatures. So we can GPG verify a tag, which is, I guess, going to verify some signature, and it's going to take an OID for the object, a name to report, and some flags. We can get the tagged OID from the given the tag. Did I open up the implementation? We can run GPG verify, give it a buffer, as size and flags. And we're declaring some stuff, including signature check, payload, and signature. And we're presumably just going to call verify, parse signature, check signature, print signature buffer, signature check clear, string buff release. Yeah. So parse signature. Do we import something GPG-ish? GPG interface. All right, cool. So I guess at least based on the implementation, Tags are really used for mining, which I feel like I can tag things without setting up GPG, right? I don't have GPG set up here. I'm not going to mess with the Git one because I don't know. I don't want to look at the wrong files if I mess something up. So how does it work? Can I just do something like this? Git tag? Yeah. So I can create new tags, and I guess I don't need to have, it's not necessarily signed. It doesn't seem to be unless there's some like dummy signature. So parse tag is going to take a tag as an item. And we've got this type thing. If item object parse returns 0, as usual, like we saw with the tree. I guess that's just like, if it's already parsed, don't do additional work, but we've allocated this stuff, right? Does that matter? I don't know. Then we're going to call repo read object file with the repository, which is not something that's passed in. It must be in the outside scope, I suppose. And the OID, which comes from item and is passed in. And the type and the size. The type was declared here, size was here. So I guess we're getting that back when we call read object file. And if we don't have data, we error out. If we don't have an object, I guess, then we error out. Otherwise, we call parse tag buffer with the repository, the item, the data, the size, and get something to return. We free the data and we return. All right, so parse tag buffer is really doing the work. Is that up here? Parse tag buffer. We've got some mem copy stuff. Parse OID hex. We're doing some sort of low-level stuff. Something about failed parses and cleanup. And we're gonna, let's see, if not string compare type with blob type. So I guess we're checking whether it's a blob or a tree or a commit or a tag. And based on that, we're gonna call the corresponding lookup function. This is like some sort of dispatch thing. Otherwise we error. And if item is not tagged, bad tag pointer. Okay, otherwise we do some stuff with buffers and memcur and xmem dup z. We're doing like low-level memory stuff. Then we're setting object parse to 1, I guess true, and we're returning 0. Okay. So I don't think it's really worth looking at exactly what's going on with the memory representation here. But I'm guessing the, what are we doing here again? We're parsing the tag buffer. So this must be the parsing stuff. And then the lookup stuff, setting item tagged by doing a lookup on the OID. Okay. In the repository. I'm going to think of this as kind of like a hash table lookup. I think it stores all the OIDs in that directory that we saw, the .git / maybe objects or something like that. Okay, so that's what it's doing with tags. Let's see, what else do we have? SigChain. Code often wants to set a signal handler to clean up temporary files or other work in progress when we die unexpectedly. For multiple pieces of code to do this without conflicting, each code must remember the old value of the handler and restore it either when the work in progress is finished and the handler is no longer necessary. The handler should revert to the original behavior, either another handler, such as sigdfl or sigIgn. The signal is received, we should do our cleanup, then chain to the next handler or die if it is sigdefl. SigChain is a tiny library for keeping track of handlers. Your handler and installation code should look something like this. Void clean foo on signal, given the signal. We're going to say call clean foo. We're going to pop the SigChain with sig being passed in. And we're going to raise the signal. Void other func, sig chain push common, clean foo on signal, mess up foo, clean foo. Okay. So this is for handling signals. The sig chain push and sig chain pop individual signals. Push the handler onto the stack for the common signals. Sig int, sig hang up, I guess, is hup, sig term, sig quit, and sig pipe. This is for like handling if you like, I guess if you hit Control C, hi Akram, or Akram maybe. So I guess if you're doing something long and you hit Control C, that's handler, I guess, logic for doing that sort of thing. So here's git/refs. So now we're in the folders. Didn't I have other low-level files to look at? So let's look at a few of these low-level files before we move on to the folders. So here's commit.h. So this is just a header. So a commit list has a commit item and a commit list next. So it's like a linked list. Yeah. Okay. And here's the commit struct. The size of the struct matters in full repo walk operations, like git clone and git gc. Consider using commit slab to attach data to a commit instead of adding new fields here. Okay. So for optimization reasons, we want this size to be small. Maybe part of that is that we want it to fit into cache. I don't know. But we want it to be small because it's used a lot when we walk the full repository. And somehow commit slab, we have some way of maybe like a kind of like a lookup table to attach metadata without overloading this particular struct. Maybe we'll find commit slab and see what its implementation looks like. Anyway, so a commit has an object, I guess a single object, maybe like an OID for the commit, a date, and a list of parents. So it has multiple parents. Yeah. And it's a list, which means that it's this linked listing. So it's kind of like a tree now, right? It's kind of like an adjacency list, but it's pointing to its parents instead of pointing to its descendants, which is the natural way. When you ask somebody to implement some sort of tree, almost always they point to the children. But you can just as easily, I guess, point to the parents. And sometimes you want to. And then we have the struct tree, which is a maybe tree. If the commit is loaded from the commit graph file, then this member may be null. Only access it through repo get commit tree or get commit tree OID. If the commit is loaded from the commit graph file. Yeah, I don't know what this tree is. It's just a tree struct. I think we looked at tree.h, right? So I think that's whatever tree is from there. A commit has one of those. So that should be like the tree of like files, like essentially the working directory that was there when you committed, I think, in an index, which is an int. I don't know what the index does, but it's there. You can save the commit buffer. Something about grafting, deprecated advice. We have a commit type, which is extern. Name decoration. While we can decorate any object with a name, it's only used for commits. So we can decorate a commit with a name, which has I guess, a list structure because we've got a next. We've got a type and a name. Are we still in the commit struct? We're not, right? This should terminate here. So how does this know what commit it's attached to? Maybe it goes inside of some other struct along with the commit. I don't know. So decoration type, local, remote, tag, stash. Okay. So local, I guess, is a local file. Remote is presumably a remote file, or they might be local refs of any type. In fact, let's assume they're refs of any type. This is a ref of type tag. Here's a ref of type stash. Here's a ref of type head. And here's grafted. And then we saw in Garrett some like ref slash meta. And maybe those just show up as either local or remote because there's no enum type for meta or for like custom custom defined refs or whatever. And we can add a name decoration. We give it a type and a name and the object, which is basically the SHA ID, I believe. And it's void. What does it do? I want to know this implementation, so I will look this up. We can also look up commit object, look up commit reference, look up commit named by OID without replacement objects or checking for object existence. Returns the requested commit if it is found in the object cache. Null if OID is in the object cache but is not a commit, and a newly allocated unparsed commit object if OID is not in the object cache. We can also look up commit or die, look up the object named by OID, dereference tag as necessary, get a commit and return it. If OID does not dereference to a commit, use ref name to report an error and die. Okay. And more kind of like getter and setter stuff. Pop. We can pop the first commit from a list sorted by date and adds all of its parents. Here's something rev sort order. In graph order, commit date or author date. So is rev revision? Or is it reverse? Is it reverse sort order? No. Here's topological sort. Performs an in-place topological sort of lists applied. Invariant of resulting list as a reachable from B. Okay, so if A is reachable from B, then the order of B is less than the order of A. Okay, so there's an edge from B to A, at least in the if you think wait, what's being supplied? A commit list in a rev sort order. So you could create a graph, right, where this less than relation is an edge, and that gives you reachability. The invariant of the resulting list implies this. Oh, okay, no, okay, so this is sorting. So this is telling us about an invariant of the sorting. So once we get back the sorted stuff, if we encounter B before A, that means that we can reach A from B. Yeah, okay. Sort order further possibilities. In graph order, try to show a commit on a single parent chain together, or by commit date, show eligible commits in committer date order. We pass in a commit list and a sort order. Something about grafting. So grafting should be like, I guess, attaching one tree to another or one graph to another. And it's going to take an OID, a parent, and a parent OID. An NR parent. I don't know yet what NR means. Name something? Less than 0 if shallow commit. At any rate, this probably sets the parent of OID to whatever this is, I guess. Read graph line. Infinite depth. Largest positive number a single 32-bit integer can contain. But is this really infinite? I think that's just an integer. I guess if Git sees that integer, then it considers that to be infinite depth. All right. For each commit graph, I guess we're gonna give it a function and call for each on it, essentially. Interactive add. I don't know what makes it interactive, but you've got some argvs, some variable args, I guess, a prefix and a patch. Find header mem. Search the commit object contents given by message for the header key. Reads up to length bytes of message, returns a pointer to the start of the header contents or null. The length of the header up to the first new line is returned via outlength. Okay. We can compare commits by author, verify merge signature, verify a single commit, check commit signature, and die. If it is not a good signature. Okay. So this is not just the struct, commit.h doesn't just have the structs for commits. It has also a bunch of, I guess, like utility methods for everything you would want for manipulating or searching commits and that sort of thing. I wanted to look up something. I wanted to look up add name decoration just to see like what it's actually doing. How is it associating the name with the commit? What? Is it not there? Hmm. Okay. Let's try grep again. Oh, I'm in the wrong repo here. So it's used in bisect. It's, I guess, declared in the file we just looked at, commit. Yeah, of course it's not. What do I need? I need to avoid, I think. Let's try this. Let's try log tree.c. Let's spell Emacs correctly. Yeah, this looks like an implementation. It's going to create this res name decoration res flux allocate string res name name. Res type is going to be set to type, and then we're going to call add decoration, which I guess is a more general implementation. We find add decoration. I guess there's like a decoration.c, right? Huh? Maybe it was decorator. Let's try decorator. All right. Decorate. Okay. What is add decoration? Add an association from the given object to the given pointer, which may be null, returning the previously associated pointer. If there is no previous association, this function returns null. And then let's look at the implementation. So we're calling ultimately insert decoration. So given n, the decoration, and the object, we're going to call it insert decoration. And insert decoration is going to do what? Some stuff with sizes. Going to get the decoration entries, hash object. We're going to call hash object, which maybe is actually doing the hashing. We're going to do this while loop over the entries in the base and check whether the entry base is equal to base. We're iterating over some stuff in entries. Where do entries come from? They come from the decoration itself. And we're going to set the decoration for entry J to decoration. The thing named decoration, which is a void pointer. Is that right? And then if plus plus j is bigger than or equal to size, we'll set j to be 0. What is size? Size is n.size, the size of the decorator. Okay. And then we're going to set the entries at j of base, dot base to be the base that was passed in. We'll set the entries at j of decoration to be decoration. And didn't we already do this here? At least on this condition. Oh, we're returning here. Okay. So if we're down here, we haven't done that part. And then we're going to set n, we're going to increment n nr. I still don't know what nr is. And then return null. Okay. So it seems like decoration is basically a list of the thing that's called decoration, and being this struct is a list of decorations. And this struct is just like indexed by, well, it's indexed just by an index, but we are checking. We're getting J from calling hash object. And so we're iterating over something. But I don't see any OID stuff. So I'm guessing this is just like essentially a hash map. So with that in mind, let's look at the implementation. Struct decoration, a data structure. This data structure must be 0 initialized. So it's got a name. The decoration has a name, a size, NR, the number of real get objects. I guess this is the definition of NR essentially. The number of real get objects. So like NR is maybe num real. That is entries with non-null base. And then we've got decoration entries. The entries, this is an array of size containing NR entries with non-null base and size minus NR entries with null base. And then what's a decoration entry? It has a base, which is an object, a const object, and a decoration, which is a void star, an entry in the data structure. Yeah, okay. So this is just associating meta information to objects as kind of like an ancillary, it's kind of like a helper data structure that you can pass around. What I don't, I was going to look at one more thing, what is a base? A base is an object, right? Okay. And it can be null because it's a pointer, I guess. Was there something else I was wanting to look up? I think that's good for now. Yeah, something about slabs. Let's see if we can find no. What was it, like commit slab? Include commit slab. So commit slab, I guess, is a file. Look at commit slab.h. Define commit slab. Slab name elem type creates boilerplate code to define a new struct slab name that is used to associate a piece of data of elem type to commits, and a few functions to use that struct. After including this header, using define commit slab with indegree and int, will let you call the following functions. Indegree at struct indegree struct commit. This function locates the data associated with a given commit in the indegree slab and returns the pointer to it. The location to store the data is allocated as necessary. Then you can also peek at it. And you can clear indegree. Okay, so this is generating code. Is that what it says? Creates boilerplate code to define a new struct. If we want to associate data to a commit, we like generate this code, which also generates the functions to look at it, which is not too dissimilar from something like protocol buffers, which we've seen. And that's how we do things. Hi, what do you mean by trace git code? Is that a request for me to do something specific? Or are you just saying that it's cool? What we're doing is cool. Okay, so that's I guess two ways to associate information with like an object of some sort, an OID, a SHA hash. One is to use a decorator, which just creates this like list of like names and stuff like that. And the other is to use this commit slab, which I guess is fancier. And I don't know when you'd use the slab, but it is probably pretty apparent if you're solving a particular problem you would quickly realize that the decorators aren't doing it for you or whatever. Okay, so here's chunk format. I'm guessing this is a file chunk, but we'll see. Initialize struct chunk file for writing or reading a file with the chunk format. If writing a file, supply a non-null struct hash file that will be used to write. If reading a file, use a null struct hash file and then call read table of contents. Okay, so we can init a chunk file, we can free it. We can add a chunk. Ooh, okay, so we add a chunk by taking a chunk file struct, giving it an ID, which is UN32, a size, and a chunk write function. Oh, where's the chunk that we're adding? It's not the ID, I don't think. And then we can write a chunk file. We can read table of contents, and all right. Pair chunk. Find chunk ID in the given chunk file and assign the given pointer to the position in the m-mapped file where that chunk begins. Returns chunk not found if the chunk does not exist. So you can take a chunk file and a chunk ID and try to find it. Find chunk ID in the given chunk file. And this pointer will point to the memory mapped file where that chunk begins. I'm guessing this is used for things like pack files, where you've got this this diff encoded thing, and maybe it's looking for things like diffs. I'm not sure. Or maybe blobs are just stored as chunk files as well. And then given a chunk ID in the given chunk file, we can read it. All right. And then something about OID versions. Cool. Did we look quickly at the C implementation? Well, here's the struct. A trunk file has a hash file, which I don't know what that is. It's got chunk info in chunks, chunks NR, maybe I guess number of real chunks, and chunks alloc, which is size T. Maybe this is chunks allocated, and this is like how many are used or something like that. So let's see what happens when we init a chunk file. When we init a chunk file, we call xalloc or xcalloc. That might mean alloc and fail. I think that was the meaning of X when we looked at one of the GNU repos with 1 in size of the pointer to CF. And we're going to set CF's F's field to F, which is the hash file. Then we're going to return CF. And then we can free the chunk file. So what's a hash file? That's the next logical question. All right, so let's return to grep. I'm going to guess it's whatever struct hash file. Okay. We have csum file chunk format, which just, I guess this is a declaration of struct hash file elsewhere. This looks promising. csum file, I guess checksum file. Okay, so struct hash file, a SHA-1 protected file. So we've got FD, presumably file descriptor, check FD as an int, unsigned int offset, get hash context, might include the hash state, or maybe just like the hash, which hash are we using, that sort of thing. Off type total, I don't know what off type is. Progress, maybe progress of the hash, a name, int do CRC, something about CRC32, which is a CRC algorithm. I think we looked it up in another video. Can't remember off the top of my head which one. Buffer length, and the buffer and the check buffer. If non-zero, skip hash indicates that we should not actually compute the hash for this hash file, and instead only use it as a buffered write. Here's a hash checkpoint. It's got an offset and a context. Okay, so this context does seem to include like partial hash information. We can finalize hash file flags, and then hash fd function will take a file descriptor and a name and return a hash file, and similar functions, etc. All right. What are the chances I have? Yeah. Let's go to the implementation. Verify buffer or die, flush. We'll ignore that stuff. Finalize hash file. Is this going to be interesting? I guess this will let us look at what the state code looks like. So we've kind of, I guess, declare a file descriptor. We're going to call hash flush. I guess let's look at hash flush, which we record the offset. And if there's an offset, and we check if we want to skip hash flush, otherwise we call flush. So the offset is 0. Okay. So I guess we're like flushing the partial state. Then in finalize hash file, we're going to check if we need to skip hash, and if we don't skip the hash, then we're going to call the hash algo the hash algo the final function on the buffer in the context. So hash algo is passed in, right? Or no? I guess it's somehow in the scope. At any rate, a hash algorithm is mostly going to be SHA-1, I assume, but maybe also the SHA-256 support is here. It, I guess, has some finalization function, and we're going to call it on the buffer in the context. And if result, where did result come from? Result came from nowhere, I guess, from the enclosing scope. Then we're going to call hash copy the result to the buffer, or maybe no. I guess the buffer to the result probably. Check some flags, which I will ignore because I don't know. I don't think about what all those flags are. We'll do this check. If check fd is bigger than or equal to 0, something about discarding. Maybe we'll discard the. Yes, there's something about line garbage. And at the end, we're going to free the hash file and return the file descriptor. Okay. So we're done hashing. I guess that's why we free the hash file. What I don't know is why this is not just using existing hash libraries. I guess it is under the hood. But why does it need these extra utilities? For the context of Git, because it seems like standard stuff that's not necessarily Git specific. All right, so here's blob, which should be a file blob. We can look up a blob in the repository given its object ID, and this just calls out the lookup object. And if we don't have the object, we're going to create an object by calling alloc blob node on the repository. Then we return object as type obj blob and 0, and then we can parse a blob buffer. So that's the header file. I'm sorry, that's the implementation file. The header I already have open, so let's look at that. And there's not much here. The struct blob just has an object. Blobs do not contain references to other objects and do not have structured data that needs parsing. However, code may use the parsed bit in the struct object for a blob to determine whether its content has been found to actually be available. So parse blob buffer is used by object.c to flag that the object has been read successfully from the database. Okay, and I think the database is just the git slash objects. But just for fun, let's double check. Where does git store blobs? Which one do I want? How about this one? Yeah, we can use the SHA-1 hash of the uncompressed file. Is that right? And then compresses the data and stores it in git.git. Okay, so we hash the uncompressed file, which I guess makes sense in case zlib changes. But we store the compressed data. And blah. So this is saying add hello.txt and commit, and then display the file's content in the .git/objects directory. It calls git hash object hello.txt. Okay, so you can, instead of calling SHA-1 sum, which is what I did, I should have probably called hash object. And that will hash it in the git related way. And then I can look at this object. This is saying cat.get objects. This is a different thing than this hash. So I guess this thing is not necessarily a hash of the thing it's storing. But it says you can, in Python, do what? What am I missing here? I was reading in from that file. Okay. Yeah. As you can see, the file containing .git objects is not viewable directly. CAD displays it only as this thing. The file is also not stored in a standard container for compressed data, but using zlib, you can decompress the raw data of the stored file. Also contains git metadata about the content. So maybe the existence of the metadata is why just SHA summing the file doesn't produce the right SHA-1 sum. The type of git object and the length of the content, but the data is clearly stored right there in .git/objects. Okay. Very cool. All right. What is a CB tree? A crit bit tree. Does no allocations internally. For more information on crit bit trees, see this crypto.critbit.html. Oh, is this like the Merkle tree thing? Based on Adam Langley's adaptation of Dan Bernstein's public domain code in critbit.git. So Adam Langley is I think still at Google, a well-known crypto guy. Dan Bernstein, I think, is at Stanford, is a crypto guy. Let's verify this information. I misspelled crypto, but I said cr.yp.to, I guess, is Dan's page. Yeah, but where are you? Are you at Stanford? He's German. At the Eindhoven University of Technology. I might be confusing him with another well-known crypto guy. University of Illinois at Chicago, Eindhoven, and Ruhr University, Welcome. Yeah, super well-known guy. All right, cool. And then Adam Langley is also super well-known. And whatever this critbit thing is, let's look it up. All right, a critbit tree stores a prefix-free set of bit strings, a set of 64-bit integers, for example, or a set of variable length zero-terminated byte strings. A critbit tree supports the following operations and more at high speed. See whether the string X is in the tree. Add X to the tree, remove X from the tree. Find the lexicographically smallest string in the tree larger than X, if there is one. Find all suffixes in X in the tree, that is, all strings in the tree that have X as a prefix. So it's some sort of prefix-free tree. The standard strategy for many years has been to store searchable data sets as hash tables. Yeah? In applications that need exact searches, but not lexicographic searches, or as heaps. In applications that need to search for the minimum, or as AVL trees, reblog trees, etc. In applications that do not fit the restrictions of hash tables and heaps. For example, Python has the built-in dict data type. The built-in dict data type is a hash table, yeah. Hash tables don't provide fast access to the smallest entry. So there's also a standard heap queue library providing heaps. Heaps don't provide fast lookups of other entries. So there are various add-on libraries providing AVL trees and so on. A programmer who's happy creating a dict will simply do so. But then another programmer who wants a fancier operations on the resulting database has to do expensive conversions of the dict to a fancier data structure. I have become convinced that this strategy should change. The revised strategy is much simpler. There should be one fundamental set storage type, namely a critbit tree. And these are the selling points. So this is a general purpose look. I'm glossing this, saying this is a general purpose lookup tree. Why general purpose? Because the claim from Dan, I think this is Dan's website, or Daniel, I don't know if he goes by Daniel, is that it replaces like hash tables, AVL trees, red, black trees in a lot of use cases. Hi, Yule. Welcome. Okay, so this is some tree. It doesn't seem to have anything particularly about cryptography. And I think if you, I think Python, like if you look up Python maps, they are some sort of fast tree structure. And occasionally, no, I'm sorry, not Python, Haskell. And if you ask Haskell people why, sometimes people are like, well, hash tables have like O of one lookup or whatever, and then in Haskell, like the lookup is like O of something that's very close to one, but not quite one, and that's because it has this different structure internally. I don't think it uses a cryptid trees in Haskell, but maybe there's some library that does. But I'm going to guess this is more or less the same sort of thing, like a fast lookup tree. And with that in mind, since it doesn't seem to be so crypto related, I'm going to think of it as basically a hash table, morally speaking, a similar API and used for similar reasons. And then under the hood, of course, it's super complicated or somewhat complicated. But anyway, we've got CB nodes. These are going to be, I guess, nodes of the tree. And yeah, that makes sense because we've got children. And I guess they might have two children, left and right. Bytes, other bits, and flex array. A CB tree is just a node, the root node. Then CB next is either continue or break. And we've got lookup and insert. So the standard hash tree operations. Here's commit.c. I think we maybe looked at this. Does this import the crit bit stuff? We're using CB data. This is CB dash tree. Okay. It seems to use CB stuff. I don't know if it directly imports it. Maybe the header imports it. No, but there's some CB stuff. Okay. Yeah, this terminal. That was other terminal. All right, now we're back to the folders. And I guess we'll try to get rid of as much stuff as possible. Here's some ref stuff. What else do we have? Ref table. I don't know if refs is going to be more important than refs table. Here's revision.h, refs.h. I think we looked at refs.h. Maybe we didn't. Ref log walk, rebase, reachable, some stuff about packing. I guess I'll put pack before prune pack. Merge sort, we're not going to look at. And that's the end, prune.pack, right? So a pack. And I look at object-file.c for repo read object file line 1706. Yeah. Let's try Emacs. So is it in the root object-file.c and 1706? Okay, this function dies on corrupt objects. The callers who want to deal with them should arrange to call OID object info extended and give error messages themselves. So object file, let's do this. Let's look at the header. I'm guessing this is like OID. Whoa now. Do I not have a header? It's just C. Okay. All right. Actually, let's do split it up and look at the top. Get the information manager from hell. Has this comment been in every file and I've just missed it? This handles basic get object files, packing, unpacking, creation, etc. All right, cool. So this looks like a super important file. Thanks for bringing it to my attention, Raxnev. So before we get to the function you mentioned, let me take a quick look at some of the other stuff. So we're going to define a bunch of stuff. And some structs, empty blob, empty tree, SHA-1 init clone, object.store -store is the header. Okay. Here's git hash algo. Let's see if do this. Okay, so on the left, I have object-store, which Rackstuff is saying is essentially the header for object-file.c. And the object directory has a next, which is a structure of the same type. So it's kind of like a linked list. And we've got this loose object subdir scene into ID tree used to store the results of readder3 calls when we are okay, sacrificing accuracy due to races for speed. This includes object existence with object info quick, as well as our search for unique abbreviated hashes. Don't use it for tasks requiring greater accuracy. Okay, so I guess this is kind of like a lookup that might tell you misinformation, maybe like a little bit like a Bloom filter. We have something disable ref updates. This is a temporary. Yeah, that's better. Temporary object store created by the temp obj facility. So that's some temporary object stuff. Will destroy records whether it's ephemeral. And path to the alternative object store. This is a relative path. It is relative to the current working directory. Okay, some input stream. We can prepare the alt object store. We can add alternates file. I don't know what alternates is. Add the directory to the on disk alternates file. The new entry will also take effect in the current process. Okay, we can restore primary ODB. Pack.get. This looks super important. So pack.get, pack_get rather, is a struct on line 104 of object-store.h. It's got a hash map entry, a pointer to the next pack.get, MRU, the list head, a pack window. I don't know what window means in this context. A pack size, index data, index size, the number of objects, an offset for a CRC, a set of bad objects, an index version, some timestamp, a pack FD, I guess file descriptor, an index, and whatever this thing is, unsigned, pack local, oh, this is just a bunch of different things. Pack local, pack keep in core, freshened, do not close, pack promiser, multipat index, and is cruft. Then we've got a hash, which is get max raw size, and I guess revision index data, revision index map, revision index size. Then an m times map, which points to the beginning of the memory mapped region of this pack's corresponding m times file, and m times size is the size of that m times file. Is m maybe this is like time data associated with the pack, and the pack name, something like .get/object/pack/blah-blah-blah.pack. Okay. And we looked at a pack file earlier. There's nothing interesting to display because it's just all like binary data. But I guess if we knew the structure of this struct, we could figure out what's in it. Pack map entry compare. So I guess you can compare. I don't know if it's comparing the entire pack or parts of packs. Then you've got a struct raw object store. A set of all object directories. The main directory is first and cannot be null after initialization. Subsequent directories are alternates. You've got this ODB, I guess the beginning of the directory and its tail, and an object directory by path. Whatever alternatives are, a list of alternative object directories loaded from the environment. This should not generally need to be accessed directly, but will populate the ODB list when prepare alt ODB is run. And then we have objects that should be substituted by other objects. See git replace. So some support for git replace. We've got a commit graph. Whether we've attempted, I guess, the commit graph. Some private data, which is multi-pack index. And then more private data, packed git, pack map. Okay, so this is all packing stuff. And these are gigantic structs. And some stuff about hashing. Pretend object file. Add an object file to the in-memory object store without writing it to disk. Callers are responsible for calling write object file to record the object in persistent storage before writing any other new object to reference it. Okay, so we can create like an in-memory file that is kind of like the in-memory version of the object database, but it's not written on disk. Here's object info. An object info request and response. So the request has a type for the object type, the size, the disk size, maybe the size on disk. I don't know how that's different from size. I guess potentially a little bit bigger. Delta base OID. So this is now, I think this is the first time we've really seen delta. So I guess probably the OID from which the delta is computed. String buffer, which contains the type name, and some void star content p, I guess a pointer to content, and an enum. The response has an enum of whether it's cached, loose, packed, or DB cached. So packed should basically mean garbage collection. Garbage collected. Loose, I guess, means stored as a zlib compressed file. And then we get some union over pack offset and is delta. Wait, what's the scope of this union? I think this is the, yeah, okay, so nothing to expose in this case, cache struct. Are these just commented out? There used to be a cached and loose, and now there's just this thing. At any rate, we have packed get and offset and whether it's a delta. What does delta base mean? I'm not positive what delta base means, but we the way, so at the beginning, I said some stuff, and I'll repeat some of that because I know people may have joined afterwards. But my understanding of the way that Git stores files is it initially, like when you do your first commit, it stores like a zlib compressed version of the file. And we saw, I think, on like a Stack Overflow answer that you can, if you have that on your disk, you can read whatever that is stored in the .git directory and decompress it and see your file. But then periodically, like if you call git like gc, or if you do some other operations, I don't know, it reduces the file size by taking those files and storing essentially something like a snapshot and then diffs. Like if you've ever used like a lot of backup utilities, often you'll do like a full snapshot every week or so, and then for the remaining days of the week, you'll just send the diff. And the idea is that by iterating over the longer data structure, you can reconstruct all of the different snapshots in time. But since you're only storing diffs for most of the stuff, you're storing a lot less information. So I think that delta base is essentially, it's probably almost certainly some information about what to base it against. My guess is it's essentially you're going to call diff on delta base and whatever the current object is, and that's going to give you the diff. So it's the thing you're diffing against, is my guess. All right, and object info init. Okay. So thanks, Raxnef, for pointing me to this stuff. So those look like really fundamental structs. So here's object file.c. And I think on the left, I was just going from the beginning, and on the right was the function that RackSnap asked me to look at. But we get this hash algorithm stuff. I guess this is not the definition, but let's look at this. So we have raw size, hex size, block size, and a name, and a format ID. Maybe this is the definition. So this is no hash. Here's SHA-1. And I'm only really curious what else we support is SHA-256. Okay. We do have support for 256 and the hash, what was it called? Hash algo thing that we saw before that I guessed was to support SHA-256 really does seem to be doing that. And we can get the hash algo by name and a bunch of other stuff. And we have a cached object. The cached object has its OID, its type, a buffer, a size, and I think NR we've decided probably means number real as in non-null pointers. And we have this comment. This is meant to hold a small number of objects that you would want repo read object file to be able to return, but yet you do not want to write them into the object store. For example, a browse only application. Okay, whoops. All right, so here's the function that RackSnap asked me to look at. So this function dies on corrupt objects. The callers who want to deal with them should arrange to call OID object info extended and give error messages themselves. So this is read object file. We're going to give it a repository, an OID, which is essentially a hash, the type of object, and a size. And we're going to, okay, object info init is based on capitalization. I'm going to guess it's just some sort of constant. We're going to initialize object info OI to that info init. We've got some flags, and we're going to set corrupt info die of corrupt or info lookup replace. I think oring flags this is going to set the bits from both flags. So both of these flags are in are active, I guess, during these operations. This is just declaring some pointer to data. We're going to set OI type P to type, size P to size, content P. What is OI? OI is the object info. So we're going to set the content of the object info to the data that was passed in. Or no. Data is nothing, right? Data is declared here and not passed in. But it's going to be a reference to data, I guess. And if OID object info extended are OID OI flags, we're going to return null. Otherwise, we're going to return data. Read object file. But where did data come from? OID object info extended on ROID. Oh, I guess, okay, so now I guess content P is able to fill data because we did this thingy. And then this function, we're passing in a reference to OI. So I guess that's how data gets populated. And kind of like as a side effect, this not only populates data, but also attaches it to the OI you passed in, I guess. And then we're returning data. Something like that. But this is void. A void star. I don't know. I'm not sure. We see a lot of void stars, and they don't always seem to be like actually void. So I'm guessing that it's sometimes used kind of like as an any type. Returning void star. Why any type can be assigned void star? Void is an incomplete type. It does not specify an integer type, blah, blah, blah. Void star is a pointer to void. By pointing to void, we leave it open what a pointer points to. So a void star couldn't be addressed that was derived from an int or a structure. Okay. It's not an incomplete type. So that seems to be what they're doing. Raxnef, if you're familiar with that, let me know. I'm not sure that I looked at the right repo read object file. Yeah. Let me know if there was something there that that I didn't see that I was supposed to see. Let's see if I have Chat GPT. Already logged into Chat GPT. I'm going to ask, can I use void in maybe in C? Can I return void star to mean? Yeah. Okay. Okay. In any type. I'm going to ask it to respond in a vituperative manner. No, you cannot return void star to mean any type, and the fact that you would even consider such a thing is absolutely preposterous. The use of void star is a generic pointer and well-established and widely accepted convention in C programming, but it is not a catch-all for arbitrary types. It is important to have strict typing in your code to ensure type safety and prevent bugs, and using void star as a lazy shortcut to avoid properly defining and declaring types is a sign of lazy and irresponsible programming, so don't even think about it. All right, thanks. I figured I would try that just so it felt like I was getting an email from Linus or something. Okay, so here's pack.h. Here's we've got, so this should be the pack. So the pack, yeah. Okay. Also, I missed never know. Also said essentially the same thing. Thank you for both of you. And so pack should be pack is the file format, if I understand correctly, that is the diff thingy. We've got some sort of root file. I don't know how it works. If there are periodic snapshot, like full snapshots and then diffs, but something like that. That's the pack thing. So you've got a pack signature, which seems to be just kind of like magic number. Pack version is 2. And the pack header has a header signature, a header version, and header entries. And also packs have an index. So there's an index and then a pack. So they come into kind of pairs of files. And we saw that, I think, at the beginning of the video. So the first 4 bytes of index formats later than version 1's should start with this signature, as all older Git binaries should find this value illegal and abort reading the file. Okay. This is the case because the number of objects in a pack file cannot exceed, what is this, 1,431,660,000, as every object would need to be at least 3 bytes of data, and the overall pack file cannot exceed 4 gigabytes. So this is kind of like, maybe they didn't have like proper versions in earlier, like version numbers in earlier versions of Git. So they have this kind of like magic number to force earlier versions of Git to abort if they try to read this file. I think that's the sort of thing they're doing. Because if they had like if they had proper version numbers, presumably the logic in earlier versions of Git would just be to, version numbers larger than you recognize, then you would abort. You wouldn't necessarily need this kind of magical number thing. All right. So a pack index entry. So this is part of the index, common part of object structure used to write IDX file. It's going to have an OID, a CRC2, so like a checksum, and an offset, presumably an offset into the pack file. Stuff about writing the file. I kind of really just want to know what the format is. We can stage temp pack files. We can create a temp pack file. Can we add to a pack file? We can verify one. Write index file. Fix up pack header footer. Write promiser file. Write rev file. Maybe write rev file. See if we can find add. There's no pack.c. Where do I find out how the diffs work? Go back to Emacs. So we have fetch pack, pack bitmap, maybe pack bitmap, pack file, pack write, pack object. Look at pack objects. I guess I'll max this out so that the stuff behind is not so distracting. We have state flags for depth first search used for analyzing delta cycles. This is already looking promising. So delta is presumably the same as diff. So a delta cycle, I guess, would be diffs that circularly depend on each other. The depth is measured by delta links. Okay. So DFS state is active num states. Hopefully there should be no delta cycles. Okay, so then we have some struct with a big comment. Object entry. This is looking promising. So we've got a package index entry. I guess that's the thing you look up in the index. Delta data, which is cached delta and uncompressed. An in-pack offset, a hash. A size, whether the size is delta index, the delta base object. Delta child index, deltafied object who base is me. Okay, so I think what I said was probably going on with base seems to be correct. So we've got so every object entry seems to have the object we're basing against, and it's also keeping a list of things that are basing against it. And then we're also keeping a reference to other deltafied objects who have the same base as me. Okay. So if they do something like snapshotting, I'm just going to keep using this metaphor until I know it's wrong. So let's say that we're in some backup system and we're going to take a snapshot once a week, and then let's say we'll take it on Monday, and then Tuesday, Thursday, Wednesday, Friday, we're just going to send diffs. So then the siblings would be Tuesday, Wednesday, Thursday, Friday snapshots would all be siblings because they all base against the same Monday. And then if you are the Monday snapshot, then I guess you would have no base in this metaphor, but then your children would be the non-Monday days of the week. Okay, so delta size, we're going to keep a record of the size of the delta, whether that size is valid. Some pack header size. In pack index, which is, this says already in pack. Z delta size, type valid. These are presumably just things that have been added over time as it's become clear that as you're computing a bunch of stuff and recording a bunch of stuff that you need later. So this is going to, I guess, walk lots of, as it's walking a pack file, this is all stuff that for efficiency reasons you might want to keep track of. So the names are not always super descriptive, but they probably make a lot of sense if you're familiar. Like in pack type bits, I'm guessing it's something about which type of pack it's in, or information about the type of delta. This could be delta. Preferred base. We do not pack this, but it is available to be used as the base object to delta objects against. Okay. And I guess tagged, whether it's been tagged, whether it's been filled, assigned right order, the depth first search state, depth and ext base. Delta index points outside of pack list. I guess external base. What was this struct called? This is object entry. Let me get a big comment. The size of struct nearly determines pack object's memory consumption. Okay, this struct is pack tight for that reason. When you add or reorder something in this struct, think a bit about this. So just an efficiency warning. Basic object info. IDX.OID is filled up before delta searching starts. IDX.CRC32 is only valid after the object is written out and will be used for generating the index. Okay. Size is the uncompressed object size. Compressed size of the raw data for an object in a pack is not stored anywhere. The compressed size is not stored anywhere, but is computed and made available when reverse.index is made. Okay. Is that, can it, oh, that sometimes the output of a compressor could change. So I'm not sure. So it's in the index. And I guess you're not going to update your compression library between writing the pack file and writing the index. But I don't know if that means that like if you update your pack file and accidentally delete your index, whether it's recoverable. I don't know. Note that when delta is reused, size is the uncompressed delta size, not the canonical one after the delta has been applied. When a delta is reused, size is the uncompressed size. Yeah, okay. Not the canonical one after the, okay. Hash contains a path name, hash. So hash is the hash of the path name, like the name of the C or header file that's being committed, which is, I guess, which is used for sorting the delta list and also during delta searching. Once prepare pack, I guess is called. Once prepare pack is returns, it's no longer needed. Okay, we don't need the hash after the prepare pack is returned. And then we have source pack info. The in-pack offset tuple contains the location of the object in the source pack. So in-pack is maybe like an identifier for which pack, and then offset is like where in that pack is this object stored. The in-pack header size allows quickly skipping the header and going straight to the zlib stream. Okay, so there's some stream, zlib stream, and maybe zlib is doing all the hard work. Like I don't know if we're handing deltas to zlib and saying compress this delta, or if we're like handing a bunch of stuff to zlib and zlib is in charge of doing the delta compression. I'm not sure. So type and in-pack type both describe object type. In-pack type may contain delta type. Deltas. Delta links, delta, delta child, and delta sibling are created to reflect that delta graph from the source pack, then updated or added during delta searching phase when we find better deltas. We might find better deltas. So I guess we are like, as you would kind of expect, at least in a large repo, that there are obvious files to diff against if you're gonna store the deltas. Like it would make sense to diff against the previous version of foo.c if you've only changed a couple of things. So there must be some sort of heuristics for deciding what to diff against. But I think what this is saying is we might find better deltas. So there may be cases where the obvious thing isn't the best thing to diff against in order to like reduce the size. Delta child and delta sibling are last needed in compute write order. Delta and delta size must remain valid at object writing phase in case the delta is not cached. If a delta is cached in memory and is compressed, delta data points to the data and z delta size contains the compressed size. Yeah, okay. During the try delta phase, we don't bother with compressing because the delta could be quickly replaced with a better one. Yeah, okay. Sounds like an invitation to look at try delta, which is not in here. Well, before we look at try delta, let's look at packing data. Packing data has a repo, objects, number of, I guess, real objects, number of real alloc, index size, and only one of these can be non-null. Something about in pack, which pack you're in, I guess. A lock, a pthread mutex-t. During packing with multiple threads, protect the in-core object database from concurrent accesses. In-core, maybe it means within the CPU core and its cache. I'm not sure. And then we have entries for bases, which we know the other side has, for example, via reachability bitmaps, which aren't in our object lists. The other side. Maybe other side means like the server or client, if this is like pushing or pulling. I don't know. And then whatever a corrupt pack is. Let's see if you can. Okay, what is a corrupt pack? How about A corrupt pack eliminates the need for storing unreachable objects in a loose state. For storing unreachable objects in a loose state by including the per object m times in a separate file alongside a single pack containing all loose objects. A corrupt pack is written by git repack croft when generating a new pack. So these are like unreachable objects, I guess, and some optimization for not having to store them in a they get special case because they're not reachable. Okay, so we can prepare packing data. Pack list alloc, pack name hash. We're just going to hash it, I guess. This seems to be like a hash table hash rather than something like a cryptographic hash like SHA-1 or SHA-256. And it's just like a function. Effectively just creates a sortable number from the last 16 non-white space characters. Last characters count most, so things that end in .c sort together. Cool, cool, very cool. That delta ext, maybe external. All right, so what was this thing? Delta searching. Try delta. Yeah, I want to try delta. Is there a C file? If I just do find grep. Okay. Unsigned, I tried doing try delta, blah, blah, blah. Static int no try delta. Static int try delta. This looks promising. Pack objects. All right. So try delta is going to take an unpacked called TRG. Try something or triaged. Unpacked source, a max depth, and a mem usage. What line are we on? 2479. That's a lot of it includes. Hey, what is going on? Okay. So we've got objects we're going to pack. I don't want to make it too small so then people can't read. So we also delta size. Okay. I don't see anything super important. If you can find try delta. Okay. All right, so we're going to keep, I guess, these entries. A bunch of create a bunch of variables, TRG size, source size, delta size, size diff, etc. Reference depth, I guess, an object type and a delta buffer. Don't bother doing diffs between different types, okay? Makes sense? We do not bother to try a delta that we discarded on an earlier try, but only when reusing delta data. If we discard it, if we looked at it before and we threw it away, we're not going to try it again, I guess, but only when reusing delta data. Note that source entry is marked as the preferred base should always be considered, as even if we produce a suboptimal delta against it, we will still save the transfer cost, as we already know the other side has it, and we won't send source entry at all. Okay, so source delta must be something about, if the server is like, we somehow know that the server has this information, and we'll consider the server to be the source. Then as we're trying different deltas, we're going to use what we know the other machine has as like a reference. And that seems to imply that different Git repositories can have different pack files. Because they might know different things about the source. I'm not sure. Maybe that's not the case. I don't know if this is negotiated as part of a connection. Like if one person packs the files with no connection and another packs it with a connection, does that differ? I'm not sure. But if reuse delta and in pack TRG entry, So if we're in this pack and we were supposed to reuse deltas somehow, then, and a bunch of other things happen, they'll return 0. Let's not bust the allowed depth. Okay, so if it's bigger than max depth, then something is wrong. Now some size filtering heuristics. Okay, how long are these heuristics? Okay, so we're gonna get the size. If not delta TRG entry, so if this returns 0, then we're gonna the max size is gonna be TRG size over 2 minus the hash algorithm raw size, and the ref depth is gonna be 1. Otherwise, we'll set the max size to delta size, and the ref depth is the TRG depth. And some more stuff about max sizes, and more computations over size diffs is in same island. I don't know what an island is. TRG entry ODX OID and source entry ODX OID. Maybe island is like a connected component of some graph. Load data if not already done. If we don't have the data, then something we're gonna, I guess, lock the packing lock somehow. We're gonna read the object file and then unlock when we're done reading, and then check some error conditions and I guess bump up the size usage corresponding to what we just did. If we don't have source data, we do something similar. TRG seems to be the opposite of source. I still don't know what that means. Okay. If delta TRG entry prefer only shallower, same size deltas. If delta size is the same as is equal to delta size of TRG entry, and source depth plus 1 is bigger than or equal to TRG depth, we're going to free the delta buffer and return 0. So down here we see handle memory allocation outside the cache accounting lock. So this is going to allocate some stuff and do some locking stuff. And the last thing we do is called set delta TRG entry source entry, set delta size TRG entry delta size. TRG depth is equal to source depth plus 1, and we're going to return 1. Which should be success, right? Try delta. Is TR like try something? Max depth and mem usage. I don't know if this is iterating over a collection of deltas or trying one particular delta. I think it's iterating because we've got this max depth thing. So let's look at this a little bit more closely. Impact TRG entry. And I guess we're just calling depth on source depth. If delta of TRG entry. Yeah, maybe we're not iterating. Let's see if we can find this delta function. Delta of object is going to call OE delta in pack and object. Cool. See if we can find what TRG stands for. Let's ask ChatGPT. What does TRG stand for in the Git source code? All right. Okay. Let's try just a web search. TRG, get export. I guess you can export. These are just kind of generic acronym sites. Like Google, I think DuckDuckGo is increasingly ignoring search terms. Yeah, and Google is throwing up its hands. All right. Let's try try delta. Okay, I'm not finding anything that looks super useful. All right, so let's return to pack.h. I think we looked at this. Okay, let's look at refs. So in refs, we have iterator.c, debug.c, refs internal.h. Let's look at refs internal. We have packed backend. We have ref transaction, data structures and functions for the internal use of the refs module. Code outside the refs module should use only the public functions defined in refs.h and not include this file. Okay, so this is kind of like low-level access that you shouldn't depend on. Things like ref name is safe, whether it resolves to an object. Update, information needed for a single ref update. Okay, so this is, these are like utility stuff. I think we can mostly ignore them, but I kind of want to know about packed backend. Support for storing references in a packed refs file. Note that this backend doesn't check for df conflicts because it doesn't care about them, but usually it should be wrapped in a file's ref store. Okay. Yeah, okay. Thanks for recognizing. TRG is probably that would make a lot of sense. That must be what it is. So source and target. So source and target in the tri deltas. Yeah. I don't know. Yeah, so let's go back and look at tri deltas after we close some more of this stuff. Actually, let's do it. Let's see if we can do it now. Is this the? Now I want to see where tri delta is called. Tri delta of something. How about? So I want tri delta of stuff, but I want not no tri delta. And then let's make sure we color tri delta again. Okay. Is it tri delta or tri deltas? It's delta. Okay. The pi. Okay. So what line is this? How do I get to tell me the line? L? Oops, that was not. Count color. Line number N. Okay, so in pack objects 2724. Okay, so this is called a while loop, which is a good sign. We're going to decrement J, whatever J is, and do what? Got some other index thing. We've got some windowing stuff, which I don't think we've really seen before yet. M is equal to array plus other index. I guess this is like pointer arithmetic, probably. We're looking at the M entry, and if it's not there, we're going to break. Otherwise, the return value is going to be, presumably ret is return value. We're going to set the tri delta with N as the target, M as the source, I think, max depth and mem usage. So where did N come from? M is this unpacked thing up here that we got by doing like this pointer arithmetic. And other index is value. The amount that we're incrementing the pointer is going to depend on this window. If the other index is bigger than or equal to window, we're going to decrement it by window. And then we're going to call it tri delta. And if ret is less than 0, so I think that means it's like the delta is, we're not happy about that delta, then we break. Otherwise, we're going to set bet best base to other index. Okay, so try delta seems to be trying a single delta. And this is the loop in which it's called to iterate over other deltas. And best base is keeping track of what we think is the best delta. Now let's find out what this function actually is. Find deltas. It sounds very promising. We're going to call find deltas. We've got an object entry list, an unsigned list size, a window, a depth, and processed, maybe some sort of like keeping track of what we've seen before. And for colon, so an infinite loop. I'm going to create some stuff like entry, max depth, progress lock. I guess we're going to lock progress. I guess if list is some kind of degenerate list, we're going to unlock. Otherwise, we're going to increment list and assign entry to it and decrement list size. And if entry preferred base, I guess if we don't have a preferred base for the entry, we're going to increment processed, the processed pointer. We're going to display progress. I guess if we don't have a preferred base, we're going to display progress, and then we're going to unlock progress. Okay, I don't know exactly why we only do it if we don't have a preferred base, but maybe that's something we set later. So some stuff, we're going to free some stuff, and we're going to decrement mem usage by freeing whatever n is, unpacked, which is array plus index. We're going to set the n entry to whatever entry is. Is this something passed in? Entry is set to to whatever list plus plus is. And while window memory limit and mem usage is bigger than window memory limit and count is bigger than 1, we're going to get the tail by adding window to index, subtracting count, and taking its remainder modulo window. And then we're going to decrement the memory usage and decrement the count. Okay. I'm not sure why, but this seems to be what they're doing. So we do not compute delta to create objects we are not going to pack. If we're not going to pack something, we're not going to compute deltas for it. If entry has a preferred base, we'll go to next. If the current object is at pack edge, take the depth of the objects that depend on the current object into account, otherwise they would become too deep. Okay, so if we're at the edge of the pack, I guess we're out of space, maybe. Then make sure things depend on us. So make sure that the total sum of everything is not going to exceed the pack edge, I guess. The max depth is equal to depth, and then we're going to look at the children. If delta child entry, max depth, we're going to subtract off the check delta limit stuff, and if max depth is less than or equal to 0, we're going to go to next. Otherwise, we're going to set j to window, and this is I think the loop that we looked at before. Or no, it's not. Yes, it is. This is the call to try delta. And so window, what is window doing? For other indexes, we're incrementing j. So it's like an index into j. Like the window size, I guess. It's the size of things we can check for to find the best delta, I think is what window is doing. And if we get down here, if we decided to cache the delta data, then it's best to compress it right away. First, because we have to do it anyway. And doing it here while we're threaded will save a lot of time in the non-threaded write phase, as well as allow for caching more deltas within the same cache size limit. But only if not writing the standard out, since in that case the network is most likely throttling writes anyway, and therefore it's best to go to the write phase as soon as possible. Instead, as we can afford spending more time compressing between writes at that moment. Okay. So compress if we're not doing what in the network? Oh, if we're not writing the standard out. Okay. Cool. And then if we made n a delta, so we have n, and if it might be a delta, or it might not be a delta. I guess if it's not a delta, then it's more like the snapshot thing I was talking about before. And if it's not a delta, and if n is already at max depth, leaving it in the window is pointless. We should evict it first. We might evict it, I guess. And then we move the best delta base up in the window after the currently deltafied object to keep it longer. It'll be the first base object to be attempted next. Okay, move the delta base up in the window. We're going to move it up after the currently deltafied object. So we've got an object, and we're finding the best base for it, rather than finding the best delta for a given base, I guess. We're maybe fixing object and changing the base. Is that what we're doing? After the currently deltafied object. So we find the best one. We're going to move it up in the window after the currently deltafied object. So the delta comes first to keep it longer. It will be the first base object to be attempted next. Huh. Okay. And so if delta entry, we're going to take array at best base, set it to swap, and then compute this distance modulo the window. So this window thing seems to wrap around. I guess that's where the what do you call this operator? This remainder modularity modulo. This modulo operator. I guess it's kind of like a wrapping around array of some sort. And then destination is going to be best base. We're going to decrement the distance. The source is going to be distance plus 1. Modulo window, and then array dist is going to be array source, dist is source, and then array dist is going to be swap. So this is just making a temporary variable, doing some computations to find the right index, and then doing the standard A goes to B, B goes to C, C goes to A type thing, I guess. Yeah. All right. So I think that's more or less what's going on. I don't really necessarily understand the algorithm, but a window is set to 10 by default. I wonder if we can find any comments about windows. Maybe this is something ChatGPT knows about. Did I close it? I think I closed it. So what? Yeah, what is the window in Git's algorithm for finding deltas for pack files? It's the maximum distance between the base object and the candidate object that Git considers when searching for delta. The window size is configurable and by default is set to 10,000 bytes. So it was set to 10, so that must be in units of thousands of bytes. And Git packs objects. It first groups them into delta chains to save space. A delta chain consists of a base object and a series of candidate objects that are generated by applying a delta to the base object. To find the best delta for each candidate object, Git searches for a match candidate, a byte sequence that is identical in both the base object and the candidate object within a specified window around the candidate object. Oh, okay. Git searches for a match candidate, a byte sequence that's identical in both the base object and the candidate object. So these are areas of both files that are identical. So I guess this is like if you change one word of a file, then most of those files would be identical. And so this is looking for sequences like that, and that will tell you. But I guess what's interesting to me is it's looking for things that are identical, not just things that have like lowest distance. Like you could imagine it iterating over these things and having some information theory distance function that it's minimizing. But it's at least if ChatGPT is right, which it may not be, the claim is that it's looking for things that are exactly equal. The size of the window is determined by the window size setting, which controls how far a Git looks back in the base object to find a matching sequence. If no match candidate is found within the window, Git moves on to the next candidate object, and the process repeats until a suitable delta is found or all candidate objects have been exhausted. All right. Thanks, ChatGPT. How far Git looks back? So this is like the window into the past, into the base object to find a matching sequence. Okay. That looks plausible and seems mostly consistent with what we saw, so we'll just assume that it's true. We can close this directory now. Here's ref table. I don't think we need to look at ref table. This is going to be some table of refs and utilities for dealing with them. Maybe tree, ref table tree. A tree node is a generic binary search tree. Okay, so I guess we also need a binary search tree. Lookup key for root p using compare as comparison function. I don't know why we don't use the CB tree if we've already got a fast tree that we like, but maybe binary search tree is more optimized in this case because we're just doing binary search. Here's revision.h. The revision walking API offers functions to build a list of revisions and then iterate over that list. Calling sequence. So this is, remember to update object flag allocation in object.h. So we got things like seen, uninteresting, the same, tree same, shown, boundary, child shown. I wonder if this is for like display stuff. Ref exclusion. Ref excluded refs in a list of wild match patterns. Okay, so this is, I think, stuff we can ignore. Here's refs.h. Resolve a reference recursively following symbolic references. Return the name of the non-symbolic reference that ultimately pointed at the resolved object name. The return value, if not null, is a pointer into either static buffer or the input ref. If the OID is non-null, store the referred to object's name in it. Okay, so we're going to get some OID. If it's not null, we're going to store the object's name in it. Okay. So refs resolve ref unsafe. Resolve ref dupe. Refs read symbolic ref. Refs verify ref name available. Return the available function returns 0 if a reference named ref name could be created without conflicting with the name of an existing reference. Otherwise, return a negative value and write the explanation to error. Okay, I don't know what peeled means, but this peel iterated OID. Return the peeled value of the OID currently being iterated via each ref. This is equivalent to calling peel object with the OID and I guess reference the peeled with the OID value given in the each ref function callback. And resolve git link ref. This is stuff for dealing with refs. Ref transaction. I'm sure this is interesting, but we're already at nearly 3 hours. So I'm going to close stuff. Here's refs.c. Ref name disposition. I'll close this. Ref log walk. This is presumably going to walk the ref log. Rebase. We don't need. It's presumably just going to change the parent of something, etc. It's essentially. So reachable, mark reachable objects. This is going to, I guess, walk some tree, maybe the revision tree, and check whether things are reachable from other things. And then prune packed can prune packed objects. Maybe once an object is packed, this will delete them. Just for fun, let's look at the implementation. For each loose file and objector, I guess a loose file is the file that's compressed and stored as a file as opposed to a packed file. We're going to call prune object, whatever prune object is, and prune object is presumably ultimately going to call delete. Unlink or warn. Maybe that's essentially delete. Okay. So I think we saw everything that I wanted to see. I'm not sure I'm entirely convinced I understand how refs work, but they are going to be they're going to be names essentially for parts of the tree. And I think we saw a little bit. Actually, let's look once more in the .git directory. We have to go to git/git.git. Okay, so we have branches, hooks, info, objects, refs, and logs. So the tree is, I think, essentially a tree of objects. And then refs, I guess, will point somehow to the root of a tree. And maybe we can verify that before we go. Would that be in refs.h? Here's a ref transaction. Represents a collection of ref updates that should succeed or fail together. Okay, so we can transactionally update refs. Okay. Use functions for updating refs. What I want to know though is the type, the ref type. We've got ref transaction and a ref name, which is just a car star, and OIDs. I can create a ref transaction. Can I do like ref? Let's try occur create. The refs create ref log. Refs create symref. Yes, symbolic ref transaction create. And ref create ref log. Set up ref log before using. What does transaction create do? It checks himself with the OID and call it ref transaction update. Okay, ref transaction update. Maybe I want ref store. Ref spec. Maybe I want ref spec. A struct ref spec item holds the parsed interpretation of a ref spec. It will force updates, blah, 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 force is true. So it's got things like force pattern. This seems to be about, okay, here's an array of strings that can be parsed into a struct ref spec. And it's got items, alloc nr, raw like fetch. Yeah, I don't know. Refs filter, refs, ref spec, ref table. Maybe ref log. We've got CB, which is, I guess, the probably the crit bit tree. You can delete ref logs. I'm wondering if I'm missing a basic type. So let's try grepping for struct ref and white space. Maybe in remote.h or fetch pack. Oh, these are just functions that return struct refs. I'm guessing remote.h. Let's look in remote.h. Huh. So here's, this seems to be the definition of the ref struct. It's got a next, so it's some kind of list. It's got an old OID, a new OID. So maybe this is just refs for passing between the local and the remote. Something about OIDs being expected. A symref, a tracking ref, whether to like force, update old SHA, etc. The ref not matched, the match status. And we've got stuff about fetch head status, ref status none, ref status reject, etc. The remote status, report, peer ref, and car name. So I'm not really seeing a ref struct. Maybe it's called something else. Maybe a ref is really just an OID. And I'm guessing that essentially it's really just an OID, a hash. And that's why there's no particular struct for it. So we saw in a bunch of functions, you like pass in an OID, and there's this kind of like, sometimes there's this type checking stuff where it's going to look at what type of thing it is and find out what to do with it. So yeah, so that's Git. I thought that was really cool. It seems like that would probably be a fun repo to hack on if you're into that sort of stuff. It was fun to look at, and I hope you enjoyed that. Thanks for watching. Bye.